So, Chau, please, the virtual floor is yours.
Okay, thank you for your introductions. Hello, everybody. I am Chau, PhD student of Professor Andrea Zealand. So today I would like to present the talk about non-parametric data-driven constitutive modeling using neural network. This talk, we will present our work on ANN-based constitutive law. And the focus in this topic is hyperelasticity in principal space, how to construct and also training the network and using it as a constitutive law for simulations. So first of all, I would like to have a brief introduction in the constitutive law. So normally when we do some experiment in the laboratory, we will apply a force on an object and it will appear a thread inside of the object. So the displacement and the force can use in the kinematics. So from the displacement we have the kinematics, we can have the trend, and from the equilibrium we can from the load we can have the stress, and the stress and the strain have different depend on the type of materials. The difference of the material can be presented mathematically using material laws. Traditionally using traditional mathematical or analytical equations, but nowadays we have a lot of data, so we can use data-driven method to doing so. It's expected that when we apply the method, we can have less computational times and more flexibilities in doing our simulations. So in the literature, we have several approach to doing so. In this slide, I present a brief review of the literature we have now in when I was in the conference last week in Oxford. So the ultimate goal is we want to achieve a model, a data-driven model, such that it can well perform in limit data, and also very easy to interrupt the results. For example, like the limit behavior, the monotonicity of the relation between the stress and the strain. In here, you can see that on the left side is will be huge amount of data. Up above will be the level of interrupt. It's easy or not to doing so. We have several approach like native neural network, possible to do the interrupt indirectly, or we can have model-free approach, require a huge amount of data, but don't need any high model or hypothesis to interpret it. Or we can use symbolic regressions. This may be get to a very long expression and difficult to optimize, but it will give quite clear interpret about the results. Or the very easy work we can do, like neural network based parameter identifications, which is not don't have any discovery at all, because we use machine learning or a neural network that as an optimization tools. So our work in the green color here, we apply we investigation some constraint of stress-strain relations and try to apply that to a neural network such that it can have a higher level of interpreted the results and reduce the data that needed for the training. So Firstly, we need to investigate how we the stress-strain relation is supposed to be. It must be obeyed some constraint. For example, here first of all, the stress-strain relationship must be have the material frame indifference material symmetry transformations. That is the most basic one that we need to have. The third one is normalizations, which means that when we mapping a principal strain to a principal stress, the principal stress at undeformed configuration must be 0 or equal some residual stress. The fourth condition is a row condition, which means that when we compress an object materials, we need a huge amount of energy to doing so. The same thing for we extend it, so it will have some asymptotic behavior. The fifth one is of this relationship is the stress is supposed to have the monotonically non-decrease, and if we take its derivative with respect to the principal strain, it have the positive semi-definite matrix. So on the data-driven approach, if we want it to improve the level of the interrupted, we need to follow those requirements, and it's quite a challenge to doing so. It's easy to see that when we applied a naive ANN as our material in simulation task, we can very likely to see the numerical instabilities or some divergent behavior of the neutron rupture during the neutron rupture procedure. We can see that there's some local strain extrema. This value will be way outside of the training range that we train the network, and also then non-zero stress state at undeformed configurations. So this challenge is usually appear when we apply a naive neural network, and is also reported in the literature as well. So in order to tackle those problems, we produce a new constraint neural network such that it can follow those behavior that we have a report and fulfill the requirements. First of all, we using with the input and the output. That the first question will come in mind when we doing data-driven methods. So we apply the eigen decompositions on the right Cauchy ring tensors such that we can receive an eigenvalue of that tensor. By doing so, we automatically fulfill the condition 1 and 2, which is the material indifferent and material transformation symmetries. And the output will be the eigenvalue of the second PLR case of stress. So with the input and output, we fulfill the first and second conditions. Now go to the row conditions and normalization conditions. That's quite hard condition to fulfill, which is have not yet reported in the literature before. So we invented a new activation function. We call it logarithmic neuron. That those neurons will assemble and create a symptomatic layer that guarantee the row condition and normalization condition as well. That we call hard constraints, which means we modify the structure of the NN such that it follows some property that we want. However, when we applied a hard constraint on a neutron network, we want to pay then no free lunch. So this network may harder to train than the naive one. So the more how control we added in, the harder it gets to train this sort of network. So in order to fulfill the fifth and or the sixth condition, we applied a soft constraint, which means that we add a term in the loss function as you see here. This is called Monotonicity, and it add another term in the loss function, so it can be called like soft constraint or weakly constraint in the term of mathematicians. So in order to employ all those constraint, our network would have followed some behavior and some trend that we wanted. After training this network, we injected in psi Phoenix. In there, we are sampling a UFL version of this network such that it can be take derivative or whatever the mathematical operator we want automatically then during the simulations. The structure of the neural network can be optimized automatically using optional or hyperparameter package very easily. So the full workflow of this work is fully automatic. Just one click and then you can have everything. Sometimes during the Newton Raphson's iteration, you get some numerical instabilities. It's because of the neural network is an approximator. It don't have or it cannot fulfill all the conditions I said above outside the training range if we just use soft constraint. Or in this work, I use hybrid method, which means that both soft and hard constraints. So maybe there's some numerical instability outside the training range. So another solution for this is employ a consistent conditions of isotropic hyperelasticities as a fallback predictors way outside the training range. I will explain later. So what is that logarithmic neuron? This is a new activation function. We invented it based on the real activation functions. As you can see in here, if we have the input less than 1, which means in the compression regime in our work, because we want to mapping the stretch from the strain to the stretch. And if the reasonable strain input is less than 1, which means we are in compressions. If it's in compressions, I applied our logarithmic function on it and have you see here this is alpha here are trainable parameters which control the strength of the asymptote. In the figure below, you can see the green line have alpha equal to 2, or blue line have alpha equal to 0.5, or you can have the idea. The stronger alpha is, the faster the asymptotic behavior behave. On the other hand, if we are in the extension regime, we don't need to do anything, just mapping directly the input to the naive network, so it can do its work to optimize. The subconstraint in the loss functions we have here is the Monotonicity constraints, which is that the derivative of the input with respect to output, and we want to parentage every negative value of it, so it will force the network to optimize for the positive value of the derivatives. And if we have a positive value of the derivative, we have a monotonicity. So however, outside the training range is a different story that we don't know. It's if we can hard constrain all the structures of the network, we can say something about the outside the training range. But if we do a hybrid method or just soft constraint method, we cannot say anything and extrapolate an AN. Always a very dangerous thing to do. So if outside the training range, there's a violation of the requirement 5 or 6, which will be lead to the local strain of stigma, and it's also lead to the numerical instabilities. So outside of this training range regime, we choose fallback predictors. In here, the choice is straightforward, just pick, because the hyperelasticity must have a consistent with the linear elastic, so that's easy to in the very small trend regime. So that is the obvious choice to pick it first. In this work, the fallback predictors only apply when it's on 3 arms outside of the training regime. So here, let's have a graph to have a general visualize what I have discussed about. So in here, we have a training on the blue light is the glow form of the stretch. The orange line is our work, and the green dot line is a naive neural network. First of all, you can have a look here and see that this our work is guaranteed to have 0 stretch at undeformed. At you can see the displacement on the vertical the axis. So 0. Sometimes we can train the naive neural network to have such properties, but it's not guaranteed. But based on the construction of our work, this is guaranteed to have exactly 0 deformation, 0 stretch state at undeformed configurations. And the second thing you can have a look here is the asymptotic behaviors of the orange lines. While the green dashed line have a little bit like a tail here, it cannot have that behavior. On the right hand side in the stretch regime, we can have a little bit at the end. We see that the green dashed line have curved downward, which means it not follow monotonicity behavior. So it's not the monotonicity, obey the monotonicity constraints. In the red and round line, you have the residue created by the NN and the glow form, and we have run the neutron eruption like on it testing, and you see at the number 5 we're quite close. So that is the ideas. This network can follow some constraint condition that we want it to do. So that's the whole theory about it, and in implementation it's quite a story for this approach. In the mindset that we want everything to be automatic and fully automation, we create a pipeline in which usually researchers in computational mechanics ignore. In here, we're training the neural network using PyTorch Lightning, which is a high-level open source, such that we can easily to scale up in our training GPU. So we can, it can just plug and play, and it's easy. The neural network hyperparameter can be optimized easily using hyperparameter framework such as Optuna. Sorry. After training, we can transfer on the trend weight and bias, and all bias we can turn off or turn on bias. So trend and send it into Phoenix. Inside that, we have Dolphin White, which is open source library that our group working on to create the eigen solver, so that we can calculate the eigenvalue of the phi by phi matrix. For in this case, I'm using it for decompose the right green Cauchy and the second hierarchy substrate, injected into NN with the weight already trained from PyTorch, and all of these is translated into UFL, which is a unified form language this one is symbolic language such that it can do automatically take derivative, and this one is will inject it into FFC. This one, this package this library will automatically generate high efficiency C code. So when we dealing with this thing, this step, there's some problem that from the UFL library, and our observation and solving this problem lead to an improvement in this library as well. Hence, everything have done, and then we do the simulation inside during the neutron eruption. We use Pepsis and direction for to solve it, well, which guarantee which provide robustness for the problems. And here is some results that I will demonstrate. For example, this is unit extensions using the neo-Hawking model as a reference and the NN predictions. In this one, the unit angle extension here at extreme case, 75% extension and no stepping. And usually when we do the linear optimization, we divide the loss step in several steps, and we do the simulation. But here, in order to demonstrate how well the NN achieve, I turn off those loss steps and only perform the simulation at once. So in here you can see on the graph there is two lines, the green line and the blue line. They are the error record from the edge line of the cube and the diagonal line of the cube. When see these two lines, we can have a general idea of the displacement field. So the difference between the NN and reference less than 4 to the power of -3, and if we can see that if we look at the relative error normal of the whole domain, we can see here is at 0.7% of error. Compression is always quite hard test for principal simulation, because they is going to the compression regime, and then in this one it demonstrates how the asymptotic behavior of the network show off. This is the compression effect, 5% compressions, and with the two line in the edge line and diagonal lines the same as the previous example, and we see that the error of less than 1.3 to the power of -3 of it. The relative error norm of the whole domain is 1.9 percentage. After that, because this is quite well performed, we want to play with something quite crazy. It's either, so here we do an arbitrary boundary condition. So we prescribe displacement in a extension 50%, and then twist it around the z-axis 10 degrees at the same time, simultaneously, and also no stepping. We can have the relative error norm over the domain will be 0.3 percentage error. Finish with the neo-Hawking and testing with the Ogden model, and this Ogden model we use with the 3-parameter version, which is quite popular, implemented in commercial software, for example, like Abacus. In this version, we have the same test performance. We perform the same test, and the relative error norm in here is still very low, 0.4 percentage. Compressions the same, and get even better error, relative error. In this case, we can see that because the input of the Ogden model also using the stretch. The stretch is the square root of the principal strand or the eigenvalue of the Ricochet strand. So this will help the neural network easier to train in this type of material. So in our case, our network is better perform on the stretch-based hyperelasticity materials. So this compression at 5%, we have 0.5% error. Extension and twisting simultaneously, only 0.7 percentage error in here. So that's on the test and the results. So I would like to summarize my thought. In this research, we try to learn the hyperelasticity material law from strand and stretch dataset in principal space using the NN. A new active differential function is invented to satisfy the constraint conditions. Monotonicity and behavior can be softly modified in the load functions. Fallback predictors can be applied and prove helpful to avoid numerical instability in the case of local extrema. And the whole in an expression using within clinic framework so that we can do the extreme case simulations. So that's all. Thank you for your attentions.
Thank you so much, Vu.
Yeah.
Clear presentation, rich of many details, but I like it because we were able to, I think, grasp what you are doing and what you are intended to do in the future.
In the future, we would like to extend it into anisotropic. So in the case of that one, it's quite easy because when we have here is 3 input and 3 output, we just extend it into 9 input and 9 output. We can achieve that.
Mm-hmm. Okay, so I'm opening the discussion. I have a couple of questions, but I will wait for our guests to ask first. Hi, Olga. Yes.
Hi. Yeah. Can I ask? Hi, everyone.
Yeah.
Thank you so much for your presentation.
Yeah.
Very, very nice. I'll probably be a little bit brief. I have another meeting to go to, but I want just to ask, so it's very relevant to what we are doing over here.
Yeah.
We have quite a large amount of data for the hyperelastic behavior. And I was wondering, what is the data that you consider? Because what we see, I think we have the largest database for the meniscus, the meniscal tissues. We have more than 300 test curves. And when we do model selection, we see that Ogden one, the one that you said, that you showed, it's okay, but it's not always that gives physical parameters. So even with the same materials, we have a huge number of models that we can consider. So one question for me to you is, what is the data that you are looking at?
The data, here is I'm looking at the principal strand.
Yeah, but from experiments or?
From experiments, maybe the stretch in 3 directions.
Okay.
The stretch in X, Y, and Z direction. With a stretch, we can do it the square, and then we can have the principal strands.
Yeah, but have you, do you have a data set, a database, something that?
Oh, I just use the synthetic data. I don't have the experiment ones. Okay, so. Yeah, only numerical generations.
Okay. Okay, that's why I was struggling to understand when you talk about data, if there were experimental data, or it was a numerical. Okay.
Yeah,
But that's fine. I think I can see what that can be done. The other thing is that we can, so my purpose is to relate mechanical parameters with architectural feature. So when we do testing, we have a huge, well, at least 4 parameters of the architecture that we consider. So we can measure the fiber dispersion, the fiber orientation. We can also volume fraction of fibers. And what we want to know, and we are working towards, is to understand what is the architectural parameters that make more impact into, mechanical parameters such as linear elastic, Young modulus, for instance. In the method that you have, is there space that you also have variables, essentially additional variables related to the architecture of the material?
That is what I intended to do in the next few months, because this is that isotropic, so it won't have that properties. But when in the next few months, I want to do in isotropic, so it would be taking account the direction of the fiber. So in that case, instead of 3 parameters like this, I will add it in the direction of vector of the fiber. So I will have like 3 components of that vector. So it becomes 6.
Yeah.
Mapping to 6, something like that.
Yeah, and each of them might be function of how the fiber are dispersed into the material, and also what is the volume fraction. I mean, you can have as many variables as you probably can, I guess. But one of the drawbacks method.
I'm sorry, I lost you.
Olga.
I'm sorry, I'm lost.
The voice went down gradually and disappeared.
Hear me now?
Oh yes, better. Maybe you pressed some button, lowered the voice. Now it's no, we cannot hear you again.
Hello.
Okay.
Okay, a little bit.
Not very far, but little low, but.
Okay.
Oh, now it's clear. Yeah.
Shout.
That's like half strong.
Oh, it's gone again.
No voice.
No voice. No voice.
No, we cannot hear you. But maybe you can write your question or comment in the abstract. Yes.
Yeah.
Please.
But maybe I think it's related to how to construct a principal space stress and strain relations. So in the case that if we use full tensors, because our derivation is taking into account the eigenvalue, which the eigenvector which is in isotropic, so it will have some special property. But if we don't take into account those one, we can still have a full tensors. We can reconstruct the full tensor of the input and output. So we don't use the eigenvalue of the strain and the eigenvalue of the stress, but instead the invariant, and taking into account the vector of the direction of the fiber, like A0 or B0, and then we can have like more invariant like I5, I6, or I7. So we still can take into account some properties of the anisotropic hyperelasticity in the same structure and the method doing like this.
All right. So I think Olga showed thumb up, so I think she's satisfied. Cannot say otherwise now.
Yeah, we can discuss through emails or chat later. Yeah.
Okay, Amit, please.
Yeah, thank you for your presentation, Vu. My question is about your fallback predictor. So you use a strain energy function for that, if I'm not wrong, yes?
This one, we just need to pick this function like this.
Yeah.
And then, because in this one, we have the lambda and mu is the lambda constant, lambda and mu is the lambda constant. So it will have some properties about material, so it won't be too much error away.
Yeah.
If we just pick some random thing, maybe too far away, so it won't guide back and back to the training regime. But based on this something like that, it will have a lot of errors, but still can guide it back because it have beautiful properties of convexity and monotonic behavior.
But would it work with will it work with all the materials? I mean, what if the material changes? Do you need to change this fallback function that you have?
Oh no, we just need this form, only this form. Whatever it we test it on linear hooking, Ogden, or everything, we can do it. Just with this one, because it's just the sole purpose of it is if there is some extreme large input, it's just guide back the Newton Raphson procedure. So it's not important at all if we have different parameter, as long as it fulfill condition 5 and 6 and it's done.
What were the conditions 5 and 6 then?
5 and 6 is the monotonicity non-decrease, and its derivative must be positive semi-definite, so we can have well posed problems.
So, so you mean, what if we change this? Have you tried other fallback functions to
yes,
see?
It can be go backs.
Will it be okay if we choose another form of function, or this is the best one?
I know I show quite arbitrary function which follow the 5 and 6, and sometimes it's longer to convert back to the training range or faster, but because this is the reason is this because of this function, because we need to have the hyperelasticity consistency with elasticity regime. So it's just a natural choice to choose that. You can choose everything as long as
just a naive idea. Maybe, but if you use the extrapolation, yeah, linear extrapolation of the
because this is actually a linear map, linearized version. This is linear version of hyperelasticity.
And I think Olga had a question: how to determine C1, C2, and C3?
It's just the eigen decompositions of the full tensors. Here, wait a minute, we will have here, right here. So you have the full tensor S and C like this, and then the eigen decompose of it is just C multiplied with these projectors. So I have here, that's here, the full tensor S. This is the principal stretch multiplied with the eigenvector, the product of it. And C i's here is the decompose of the full tensor C, the big C here. And when I decompose it becomes C multiplied with the eigenprojector, which is the product of the eigenvector. This is the eigenvalue. This is the eigenvector. So it's just a decomposition we use using Donvin-White library in here. This one we'll publish it in the near future, so we can have these. So all everything will be decomposed and fully in the UFL language, so that this whole framework of Phoenix X can take the derivative of it. But pay attention that because we also do the decomposition, which is highly nonlinear, and then we injected it into the NN. Again, it's highly nonlinear. So this is a massive symbolic way, maybe several pages, and then when we convert it into UFL and generate the CC code here, it's quite a problem. So we also need to an improvement in this thing to make Habra in our group, and also Professor Zealand. So we invest a lot of effort into make it happen. Yeah.
I have just one more question about this fallback predictor. What if you have these Lamé constants?
Lamé constant, because I use...
You could get it from your data, maybe, but...
Yes, this is because I use the numerical simulation, so everything I known before. In this one, we can say have this mu for hyperelasticity is calculated from the Poisson ratio. So if I just show some physics realistic thing like 0.3 or 0.4, don't necessary to be exactly the one in the data. It still work because it's just the sole purpose of it is numerical stuff. It won't do any don't have effect in the accuracy of our neuron equation like in here. Because when it works, it activates when it's outside the training range. And outside the training range, we for sure we cannot make it correct prediction. So everything must be inside training range, so we can show on the properties obey.
Yeah.
So yeah.
But couldn't it be the case? Could it be the case that you can take this without Lamé constants based on taking the derivative of your of the A and N, or maybe numerically, just choosing two very close by point and take the tangent, and then use the extrapolation without any extrapolation without any function, a specific function. The function will be very linear.
So I got the idea. So it may be linearized.
Right now here you have a function that it might bring the questions. What if you don't have this function? Because we are working on data-driven cases.
Yeah.
In future, maybe you don't have the function.
Yeah, maybe. Yeah, that's quite interesting idea. Maybe that take the linearize at the end when the
at the edge of the border.
The training range
and training range you take.
And I can have linearized, so it's still positive, definite. Yes, that's correct. I still have that one.
Yeah.
Interesting idea. Yeah. Thank you.
You're welcome.
I cannot see the raised hand, so maybe I will use that opportunity to ask my question.
Yeah.
I have a few, but questions about the choice, or maybe about your comment on my questions. So maybe first is this monotonicity constraint that you are applying, the F over DC, which I think is present on slide 7 for the first time. Exactly. So it involves the derivative of your output from your neural network with respect to the input.
Yes.
And by doing it so, you are practically involving all the weights of your neural network in the loss function. So when after computing this ds over dc, most right-hand side part of the expression, so have within this loss function, you have already all weights of your neural network mixed together.
Yeah, it's
So,
huge. It's computational expensive.
Yes, this was actually my question, because normally the gain, one of the gains of artificial neural network is that you can apply this backpropagation procedure, which is
Yes.
computationally very efficient and is scalable and so on and so forth.
Yes.
And by applying this sort of constraint, you are killing is one of these advantages of the neural networks.
Yeah,
of course, it doesn't hurt at the prediction time, but for the training, I believe that it might be a kind of painful aspect.
That's the case for 2 years ago. Last year, the PyTorch library has been improved a lot, and then nowadays, I remember that like 1 year and a half when I do this operator, it will 30 times more expensive than a normal one, but nowadays it's just 2 times. It's quite really impressive improvement in the PyTorch library. I don't know for the others.
I see. And how many layers do you have in your neural network?
You see how many?
For a normal one.
Pardon, because you were cut. Can you repeat? Can you
I'm
repeat?
sorry, I'm sorry, I lost you.
You were cut for a while.
Okay. Yeah.
So how many layers do you
Connect your cable.
this-
Connect your LAN cable. Maybe it would be better.
Yeah. I forgot the adapter.
Okay, don't worry.
So this, yeah. So actually, this operator is not expensive, as expensive anymore. Now it just took me double the times in comparison without it, because the huge improvement in the PyTorch library. So I take advantage of it.
How many layers in your neural network do you use? Like,
For example, in this
layers.
work, I only took 2 layers here.
Okay.
And 1 layer for the asymptotic layer.
And that's why it's not
cheap.
really expensive. But if your neural network is bigger, I think that would make it more expensive, the derivation.
No problem at all, because for nowadays the machine learning, like the normal flow or transformers in the natural language processing, they all take derivative bit, and that's why they have a huge investment on taking derivative, so that it's now only double time. Then maybe I don't implement it correctly. Maybe it can be faster.
Okay. And my second question, is about this log operator, log activation function, which
yes,
this is like puzzling to me. So I want to dig a bit more why you made this choice about the placement of this nonlinear operator. I would say I call it. I guess that the reason why you did so is that you wanted to achieve this nice property of your constitutive relationship, that for the 100% compression, you will have infinite force, right? But why did you put this as an activation function, not as a part of the loss function? If you could trace back to the slide number 8 or 7, I don't remember, when in which you present, here. You presented your loss function. You have this S I minus S dash I, right?
Yes.
So you could easily, I guess, apply it here, right? This logarithmic
it can.
operator for this S I, that their output of your neural network, you could apply this logarithmic thing and compare it to the data, and then you could capture this non-linearity in that way. Putting this as one of the neural network layers is more difficult to me to, let's say, process in my mind. It doesn't mean that it is wrong. Maybe it is brilliant, but I want to hear your comment.
I understand that. So naturally, when we approach to using the neural network, maybe we want to try to keep the standard structures, and then we push our constraint into the loss function. So that approach called soft constraint. And soft constraints is not guaranteed the property that we want. In the training range, it may very likely that can follow our constraint because we train on it. But outside the training range, so for example, here the training range is from 0.25, so from minus in the x direction you see from minus 0.5 to positive 0.5. That's a training range. And inside that range, you see everything is for example, in a green line. You see, the green line is the native one, and using the soft constraint. So it follows everything very well. But outside it, from minus 0.5 to the left, it don't follow the asymptotic behavior anymore. That's the reason when you see the orange line is it follow quite well. So the hard constraint, this changing the structure of the network is a hard constraint, and it will somehow guarantee for us the properties of the network outside the training range.
So this
it's a guarantee.
This I understand that you want to put hard constraint, but my question was why didn't you put this reparameterization of your variables to the end of your output, like applying this directly on S, not as to some layers of your network. That's the question. What's the difference? What's the reason?
Because when the output need free at the end is a linear mapping from minus infinity to positive infinity, and we flexibility have a lot of flexibilities. And when I inject the input into this asymptotic layer, and it will be inject after apply that one, it will inject to the normal NN structures. By doing so, the normal structure of the NN can adapt with the asymptotic layer. As I mentioned before, the hard constraint will affect a lot on the abilities of the learning of the network. So if we put it at the end, it don't have anything else to. I mean, it will be experience. It will be super hard to make the network to learn. So
maybe a comment from my side on that. So first of all, I think I disagree with the argument that you could incorporate this asymptotic behavior into the loss function. I think that is a misconception, because the network itself has a certain predictive capability. And if you just take a simple feed-forward neural network without any special thing, let's say a common activation function used there, you could go with some tanh, for instance, because you would like to map or to learn a nonlinear function, then there is no way of incorporating this asymptotic behavior in the loss, because in the end of the day, you would like to match your data. So you would like to have a good curve fit. So in order to have the predictive capability of the network to, just in case, predict this asymptotic behavior as well, something needs to be done to the architecture of the network. Wu showed this deficient behavior of a simple feed-forward neural network in the graph, where you could see this, what he described as a tail behavior. Yeah, so you cannot get rid of this green tail, which is simply there. It's like a leftover of the network prediction outside, and here in this case left of the data range. The data range, I think, is something between 0.5 and 1.5 for the squared stretch, something like that. So you cannot have this asymptotic behavior with a multi-layer perception. So the fix that Wu came up with here is simply based on the idea, or by inspection of the mathematical properties of what your multi-layer network has. So if you project the incoming input automatically to, let's say, enforce that asymptotic behavior, that is one way of, by construction, imposing such an asymptotic behavior. So whatever input you get pretty close to zero, it will always be pushed to a very large negative value, whatever happens in the network layers that come later. Okay?
I see.
So it's like an,
I think now I'm getting the.
it's by construction imposed that behavior. And in fact, a similar thing could be thought of the other growth condition for larger stretches. Yeah. However, one has to think about that very carefully, because it's simple to see here for the one-dimensional case. It might be not as easy for the higher dimensional case. So that requires a bit more rigor. But our observation so far is that things, or trying to impose constraints that you identify in the course of your work with neural networks, using, let's say, the weak approach, is problematic, because you change your cost function that you want to minimize, so it has a huge impact on the optimizer. I think the other approach of hardly incorporating this, meaning by construction of the neural network, is way more favorable, but more difficult. Because, and in the end of the day, you could ask, what are you actually doing? Is it still like close to model free, or have you incorporated all your available knowledge just to have some reasonable curve fit that you could better do with a maybe slightly more costly strain energy function and a very classical approach?
Yeah, may I also add another comment?
Yeah, yes.
We'll go to this logarithmic thing that you have. Okay, the figure below shows it's the output versus different inputs, yeah?
Yeah.
The activation, one very important function that these activation functions have is that at some point it deactives a neuron, which means that it is not the output of a neuron within outside of a specific interval will be zero or a very specified value. That's how it makes it like piecewise interpolation. But what I cannot see here is this feature, because the neuron, the output of neuron varies, sometimes more, but sometimes less, sometimes non-linear, sometimes linear. But I don't see any deactive area or any deactive interval for this activation function.
What
you see ReLU, like you see,
yes,
you see ReLU, at some point it becomes zero. Or
yeah,
you see other functions, at some point it becomes it becomes zero if you like, for example, ReLU, it becomes zero if you go below x equal 1 or something. Yes,
yes,
plateau, it's all zero. Yeah, or others, like maybe not zero, but it becomes 1 or -1 at some place, which we call like deactive neurons. But I don't see this function specifically here.
Yeah, because this
always
one
sensitive to the input. It's also it is always sensitive to the input. But when you have activation functions, they should be non-sensitive to the inputs at some point. That's how we call it like deactive.
No, this is a layer that we want it to be sensitive like this way. We don't want it to be general. We want it to be have an asymptotic behavior when the input is less than 1, or when you scale the input, you need to do the chain base of a logarithmic function. But the general idea is we want it to have this behavior when it have less than 1, and then exactly 0 when it equal to 1. So if x is 1, it's exactly 0. Yes,
yeah, but it is only 1. If it is only 1, it is exactly 0.
Yes.
But not like if it is below 1, it is exactly.
Yes. If it's below 1, so it will have this asymptotic behavior like
And if
1.
it is
Yes.
above 1, it will have a linear.
Yes, it's the linear mapping. So we can put it
But this means that the neuron never deactives. It's always active, the neuron.
Maybe this is just a matter of naming convention, because I guess that the reason why Chau chose it is that it is just a reparametrization of his input. So he could do this as a pre-processing, I guess.
It kind of
on the C data
space of principal space.
Instead of C, he could input to his neural network log of this logarithmic transformation of C, and the remaining part of the neural network would remain the same with this standard activation function. And this is only a trick in order to have this incompressibility asymptotic behavior. It's even taken away from the neural network part, I guess, and this would work as well, right?
But it's important to make it become an activation function because it needs to get the derivative of it as well, so that the network can learn. Otherwise, if we just do like a scaling, like outside, like scale, min-max scaler, something like that, it won't learn that thing. So, because when it take this alpha here is trainable, so the strength, you see, the strength of the asymptotic behavior is decided by this alpha, and this alpha need to be trained. So by make it as an activation function, we can train this alpha as well. So because we have no idea how because for example, if rubbers, it look like the green line, but it's soft adhesive, it will look like the blue line because it's softer. So the important thing is we also need it to be this alpha to be trained. It's not just logarithmic space.
But
it's
this would be more expensive than typical activation functions, isn't it?
It's similar to ReLU. ReLU is X here and then 0 everywhere else. This one just apply, but it's obviously less expensive than sigmoid or tan edge or some smooth curve. Yeah. So
but
it's not.
Maybe you could also add a deactive area and try it. Just try it. Try to add a deactive area or an active interval. Let's say like between 0.5 to 1, it's logarithmic. Between 1 to 1.5 is linear, and after 1.5, it's, I don't know, 1 or
can do that. Yes.
And then below 0.5, it's also a specific constant value.
Yeah.
That would add this feature of being deactive.
Okay. So I think we are already about the time that is allotted for the seminar. So we should be slowly finishing. We have space for a very short comment or question, but otherwise.
Yeah.
Can have the continuation of the discussion afterwards directly with you or Andreas. All right, so thank you so much, Wu and Andreas, for preparing and showing this nice topic. And thank you, everybody, for your attention and for the comments and questions. Have a good day, and we'll see each other, I think, in 2 weeks.
See you. Thank you. Have a nice day. Bye-bye.
Thank you. Goodbye.